Welcome back, science students. Today, we're going to look at the cosmos, but not just through the lens of a telescope. We're looking through the rather unforgiving lens of mathematics. Let's jump right into this explainer on the statistical realities underlying astrobiology and the search for extraterrestrial intelligence. We're going to figure out exactly why our universe seems absolutely teeming with planets, yet totally devoid of advanced neighbors. We've got to begin with the famous Fermi paradox. It's a question that's been haunting astronomy for decades, right? It confronts the literally deafening silence of the cosmos, despite its incredibly vast scale. I mean, we know the raw ingredients for life are everywhere. We know there's been plenty of time for advanced civilizations to rise up. So, if the universe is so vast, where is everyone? Well, to answer that, we really have to rethink how life survives. Here's our syllabus for today's explainer. 1. Silence in a crowded universe. 2. The mathematics of bees. 3. The statistics of survival. 4. NASA's search for biosignatures. And 5. Interpreting the cosmic data. Section 1. Silence in a crowded universe. Let's set the stage by looking at the raw observational numbers we're currently dealing with in modern astronomy. Just think about this number for a second. 6,000. NASA has now officially confirmed over 6,000 exoplanets orbiting other stars. And honestly, that is just a tiny, tiny fraction of what's actually out there. This data proves beyond a shadow of a doubt that the planetary raw materials for life, the rocky worlds, the habitable zones, they are incredibly abundant. The universe is practically overflowing with real estate. Yet when we apply the famous Drake equation, which is the probabilistic formula used to estimate the number of communicative extraterrestrial civilizations in our Milky Way, we basically hit a brick wall. We plug in the rate of star formation, the high fraction of stars with planets, the planets with the right conditions, and we're left scratching our heads wondering why we haven't detected a single communicative society. Something in this equation is relentlessly driving that final variable to zero. Okay, moving on to Section 2, the mathematics of bees. Before we keep looking to the stars for intelligent communication, let's actually examine a fascinating first contact story right here on Earth. So our story takes place in rural Austria back in the early 1900s. Now, for thousands of years, humans essentially thought of bees as little biological robots, right? Just mindless insects doomed to dreary industry. But a scientist named Carl von Frisch, he wanted to understand how these seemingly simple creatures could actively communicate the complex spatial coordinates of food sources to their hive mates, even when that food was kilometers away and had zero recognizable scent. Well, von Frisch's experiments revealed something absolutely mind-blowing. The bee dance is actually a complex mathematical equation synthesizing astronomy and time. Check this out. Step 1, an upward angle means fly toward the sun. Step 2, the left and right swivels convey the exact spatial coordinates. And step 3, the duration of the dance calculates the travel time down to a fraction of a second. They even factor in wind speed. So think about it. If Earthbound communication requires this much evolutionary precision just to find pollen, what kind of biological miracle is required to build a radio telescope for interstellar signaling? Which brings us perfectly to Section 3, the statistics of survival. If biological complexity is that mathematically precise, we need to totally reframe evolution. It's not some gentle, inevitable progression toward intelligence. It is a brutal gauntlet. This introduces the concept of the Great Filter. This theory suggests there's a universally pervasive probability barrier made up of highly improbable evolutionary transitions, or just catastrophic existential threats, that almost no life can pass through. It's essentially the universe's ultimate bottleneck. And this filter operates on cold, hard math. The survival of any candidate galactic species is subject to a power law distribution known as Lotka's law. Lotka's law shows us that the frequency of surviving species diminishes exponentially with every successive threat they face. The statistical drop-off is unimaginably steep. You have to think of evolutionary survival as a win-or-lose tournament. Survival is purely binary. You win or you go extinct. It's exactly like a PGA golf tournament where you have to win consistently just to stay on the tour, or like fighter pilots in successive dogfights. If a pilot loses a dogfight, they don't get to fly again. A species has to survive the cumulative statistics of ongoing, relentless hazards, asteroids, climate shifts, resource depletion, self-destruction.
Under Lotka's law, the number of species capable of surviving a long succession of these binary survival challenges shrinks down to a tiny, tiny fraction.
Section 4. NASA's search for biosignatures. So, how do we take these really harsh theoretical survival statistics and apply them to our ongoing empirical research?
Well, this duality changes everything about what we expect to find. Using incredible tools like the James Webb Space Telescope, we're actively hunting for two very distinct targets in the atmospheres of distant exoplanets. On one hand, we have biosignatures. These are gases like oxygen or methane produced by simple biological life. And on the other hand, we have technosignatures, which would be artificial chemicals or radio waves produced by advanced industrial civilizations. To find these unbelievably rare technosignatures, we are pulling in a staggering amount of data. Initiatives like Breakthrough Listen have already released 1 million gigabytes of data. They're rapidly analyzing the cosmos across a massive range of frequencies, hunting for any artificial anomaly. We are basically sifting through a cosmic haystack at blinding speeds, looking for the absolute rarest of survivors.
Finally, Section 5, interpreting the cosmic data. Now, considering everything we've just covered, what's the crucial point you should be taking away from this synthesis of biology, statistics, and astronomy?
Here is the ultimate takeaway. When we analyze planetary biosignatures through the lens of Lotka's statistical survival, our expectations have to diverge wildly. Because of the brutal statistical drop-off dictated by Lotka's law, we should absolutely expect our telescopes to find primitive microbial biosignatures long before we ever detect a technosignature. Simple life only has to survive those first few evolutionary challenges. But advanced technosignatures, statistically requiring thousands of consecutive binary survival wins, makes them exceedingly rare.
But hey, we can't let the mouth defeat our curiosity, right? As Giuseppe Cocconi and Philip Morrison famously noted back in 1959 regarding the search for extraterrestrial intelligence, the probability of success is difficult to estimate, but if we never search, the chance of success is zero. We have to boldly continue observing, launching new telescopes, and searching the cosmos totally regardless of the daunting statistical odds stacked against advanced life.
I'm going to leave you with this one final, pretty sobering thought to chew on as you consider the statistical gauntlet of life. If we ever do detect an advanced civilization, if we ever capture a technosignature or a radio wave from the dark, what terrifying gauntlet must they have survived to send that signal? And perhaps more importantly, what could they teach us about surviving our own? Keep looking up, everyone, and keep doing the math.